Welcome back, everyone. It's a pleasure to introduce the second speaker for this morning, Professor John King. So we'll continue his lectures. And since we're starting 10 minutes later, you have the freedom to end 10 minutes after.
Thank you. I've very much enjoyed this week so far. I will actually attempt to get us back onto timing, but let's see how it goes. So the first thing I want to do has got nothing to do with today's talk. These are the pictures associated with the first talk yesterday. As is clear, I've been extremely lazy and just extracted the relevant pages from the papers. So there's two sets. The first set is the Darcy flow case, the Healy-Shaw case in the otherwise ill-posed situation where you're extracting fluid, in this case to do with cells degrading. But there is the growing rim balancing that. And there's also the kinetic undercooling condition stabilizing it to some degree. The numerics also put in surface tension to help out a bit. So this with Joe Isles and Vanessa Stiles at Sussex. If you ask me any questions about this, I'm going to have to read what it says. So I propose just to flick through them. So the top picture, at least, is the left-hand side is the initial data where you're perturbing off the spherical case. The middle one is a regime where I don't know why I'm pointing at the screen. The middle one is a regime where the circular solution is stable, and the right-hand picture is where it's unstable. So it's starting to elongate. And then there's a sequence of pictures showing lobes develop. So there's clear instabilities. The morphologies aren't quite the most familiar ones, I think. I don't know. I'm not sure I want to flag any of the others. I am going to very quickly scroll through them. So you get a range of different shapes, asymmetric thing at the bottom, also done 3D, and you get things looking a bit like red blood cells, although it's got nothing to do with it. This is now maybe Stokes, is it? Right, so the other set of simulations are with Shaker Venkataraman, again at Sussex, in the Stokes flow case. These are the less interesting ones. I think that's the shape-preserving thing I mentioned. No, that one can't be. Let me get to the more interesting ones. So remember that this is now, I've gone from the shape-preserving case, which is when the thing's growing, to the competition between degradation in the core and growth in the rim, where you get this buckling instability associated with the compressive stresses in the rim. So you're starting to see them in the bottom picture, but the top one here is the most instructive one. So this is a different mechanism for fingering instabilities, and they're a very different type. But the code breaks if you try and take it beyond that point. So we're trying to refine it beyond that. I'm not sure I want to mention any of the others. Okay, so that was that, unless there are any questions about those. Okay. And I can't find the talk because it's hidden behind the hot top. I need to get rid of the bar at the top so I can open the other PDF.
Let's see. Is it up there?
Oh, well done. Yep, thank you. Thank you. I may need to move it back again though. You just, okay. Right, so I was going to make some introductory comments that which is why that doesn't have a formal start to it. But I'm going to cut down on those. So I'm going to talk about quasilinear reaction diffusion in a rather general form. Okay, so nonlinearity both in the source term, which in the previous talks were associated with cell division, and with the transport term, which earlier I derived primarily on the basis of mechanics, right? So that's not got a standard derivation. So we saw equations of that class from various different contexts yesterday. Beyond that, I'm going to start from scratch now. I'll occasionally refer back to the tissue growth context, but view this as a talk primarily on the mathematics of that equation. and formal analysis, to be clear. There's lots of rigorous questions still open. The introductory comments I was going to make, I will summarize in the following way. So with these scalar equations, there's two main classes of traveling wave phenomena. One is associated with a wave connecting two different stable states, so heteroclinic. You can write this as a gradient flow. So in that situation, the state with lower energy will overrun the one with higher energy. That's not what I'm going to talk about. I'm going to talk about the connections between a stable state and an unstable one. So the classic paradigm is the thing that's now on the screen, Fisher's equation, or KPP. So two papers in 1937 kind of kicked off a big pile of nonlinear analysis of PDEs. It was a very early stage of this. The scenario I'm describing through Fisher's equation is the one I'm going to talk about throughout. So solving the equation on the full real line. Throughout the talk, U equals, there's two uniform steady states. U equals 0 will be the unstable one. U equals 1 in the tissue growth context, the close packed case will be the stable one. So you think, again, to make some connections before, you're thinking about having an initial small blob of tissue dilute well below the close packed level, and then the equation will tell you it lifts off towards 1 and triggers off traveling waves in two different directions. So the wave speed for Fisher is, this is kind of famous, and familiarity maybe breeds contempt with this. It's slightly surprising that there's a very simple explicit form for the wave speed for a nonlinear problem. And the reason for that is going to be implicit in a more general context later. The other thing to say again is this close pack business I want to emphasize in the talk. So with Fisher, by comparison principle, simplest way of saying comparison principle with the ODE version, if you start below 1, you can never hit 1. So you never get to close packed with this equation. With some of the others you do, which I'll come to. And even if you started close packed, because the linear wave propagate, the linear heat operator has infinite speed of propagation, you'll move away straight away from close packing. So that's the classic paradigm, but I'm going to be talking about situations which don't simply behave in that way. So how am I going to generalize? Well, obviously can't say very much concretely if D and F are completely general. So I'm going to do the power law case. So positive exponents representative of increasing functions, negative of decreasing functions. So we've got these two states, and I'm going to have power laws at each end. So the power laws can be different. So the subscript F means front and B means back. I'll often drop the subscripts where I hope it's clear. But power laws in each case, P is typically always going to be positive because the cell division rate better not blow up. Although I should say there will be far too much information in this talk, but I did want to try and cover the whole story in some sense. I'll try and highlight the key points. So P positive is the most important case, but the N's can be positive or negative. And I want to be explicit in seeing which case we're dealing with. So M is minus N. And wherever an M or an N appears, those will be positive. V is 1 minus U. So that's, if you're thinking about the behavior local to the wave back rather than the wave front, you want to deal with V rather than U. We saw this yesterday, but it's just a reminder of what this might have to do with tissue growth. It was the simplest context in which I derived a reaction diffusion equation. So continuity equation, cell birth, velocity field by Darcy gives you a very general nonlinearity for the diffusivity, which is why I got interested in doing these rather general cases. Okay, so I'm going to try and talk you through the way I try and understand this kind of problem. And one of the first steps I always make is to split the problem into its component parts and then try and put it back together again. So the next few slides cross out one of the terms in the PDE and see what you get left with. Okay, so the first is to understand what the nonlinear diffusion terms do. So I cross off the source term. The top equation's got literally thousands of papers. The second one probably hundreds. So the first one's called the porous medium equation. The diffusivity vanishes as U goes to 0. And that leads to this finite propagation speed property. So the easiest one to visualize is M equals 3, which is a viscous fluid drop on a horizontal surface. So it spreads at a finite speed. There's a interface, a free boundary separating the wet part and the dry part. Conversely, if n is negative and you can't make it too singular or there's no solution, you get fat tail behavior instead, and the Gaussian, the heat equation, sits in between those two. So that was crossing off the source term. If I cross off the diffusion term and just talk about the ordinary differential equation in time, P is positive, P bigger than 1, you've got finite time blow up. Okay, so a classic undergraduate example, I guess. That does carry over to the PDE as recorded there, except that if you've got this inequality between P and M, the diffusion term can be strong enough to prevent the blow up if the initial data is small enough. Okay, but the ODE property does get inherited by the PDE as long as you're careful about regimes. The converse case, and this again, this is at the wave front, I'll do the wave back in a minute. At the wave front, if P is less than 1, you've got the classic non-uniqueness, non-Lipschitz business, where the solution can kick off at any finite time. Now, for most of the regimes of the PDE, that's not a case that's going to arise because the diffusion term will kick off growth at infinity, even if the solution starts off 0 there. But because of the property I referred to on the previous slide with M positive, you can have situations where the solution does hit 0 at finite distance for all time, rather than the non-Lipschitz source term kicking the growth up. So again, one can infer something for the PDE from the ODE. I referred to Gompertz yesterday. This is a complete aside, but I find it quite interesting that there's these two different regimes, but there's one special case, P equals 1, the linear case, where neither of these things happen. So the borderline is a slightly odd one, and the nonlinearities close to that borderline that have the same property as P equals 1 are ones involving U and then logarithmic dependencies on U. Okay, so Gompertz is viewed as having some biological meaning, but this is a purely mathematical implication of it. Okay, so the corresponding analysis of the wave back, the only case I need to refer to is P less than 1. So remember, V is 1 minus U. So the additional phenomenon that can occur there is finite term extinction, as recorded by that formula. And that, again, can be inherited by the PDE in suitable ranges of n. So the solution can touch down at a point, and then that point can spread out for a finite region with V0, so a dead core. So I'm not up to date on the mathematical literature of the dependence of this phenomenon on N and P. So that if anyone is, please talk to me about it. But that effect will be associated with close packing later on, right? So if a dead core develops, V equals 0 corresponds to U equals 1. So to close packed cells. So that's almost all the possible limits. There's one more where you cross off the time derivative. So you get an elliptic problem, if you like. I flagged two properties in this case, which are going to reappear later. The easy one to see is this equation does have a power law solution as recorded there, which will correspond to local behavior at interfaces in things I say later. And then the top one is to do with this dead core business, except it's not quite a dead core. It's trying to form a dead core with a minimum of V in that central point, but with a singular behavior on the two edges. So a priori, this doesn't look like it's going to play any physical role, but it will do in the sense of matched asymptotics, where you smooth off that singularity. That'll be an outer solution. You smooth it off over an inner region. Okay. So a lot of the talk will be on ordinary traveling waves, so waves that travel with finite speed. The things I'm most interested in are not that case, the superlinear growth cases, which we'll see later. So this kind of case is well understood. I'm going to, I guess, add a few extra results to what's known, but primarily it's to feed into what I say later. So for the one of the key concepts, but I'm going to claim right at the end that this is not the best way to think about these kind of things, is pulled against push fronts. So pull fronts are what happens in Fisher's equation. The wave speed is explicit as 2 because the solution is dragged forward by the region where u is small and where you can linearize the PDE. And you understand that either by drawing the phase plane for the traveling wave ODE, which I'm going to do in a minute, or you use Liouville-Green, what some people call WKB method, to derive a Hamilton-Jacobi equation from the PDE, and then you analyze that. But both of those are based on a linearized analysis of the PDE. You can also get push waves, and again, this will be clearer when I draw the phase plane in a minute, where the speed is greater than 2, because it's the entire wave profile that matters, not just what's happening at the leading edge of the wave. One of my punchlines at the end is that pull fronts are dragged along by the wave front, pushed, driven by the entire wave profile. I'm going to come to situations where the solution is driven by the wave back. So it's sort of the converse to pulled. And I don't think that's widely recognized as a phenomenon. Okay, so that's the comment at the bottom. One final simple connection to the things I said yesterday. The simplest example of all, I think, of push and pull fronts is you take the linear PDE wherever the solution is in close pack, so n less than 1, and then you have some finite wave back at which n is 1, and at which you're pumping in extra material, this flux J. So that will correspond to cell division in the close pack region, which sits behind x equals s and pumps in material at a given rate. So it's, of course, explicit because you can write down the traveling wave ODE and it's linear, and Z throughout will be the shifted coordinate x, which is moving with the wave speed. Okay, so you always, right, so there is a continuum of waves. That's one of the complications with the stable-unstable connections you don't get with stable-stable, where you've got an eigenvalue problem. So with the stable-unstable, there are waves that go any speed faster than the minimum speed. But if the initial data decays fast enough, you get the minimum speed. So you can view the minimum speed as kind of the generic outcome. All the others you have to force in a very special way. Okay, so you do that calculation, you make the solution to this ODE decay as fast as you can. If J is less than 1, you find you sit on the critically damped case for simple harmonic motion. So the solution is recorded there. There's a degenerate node at the origin, and I'll draw relevant phase planes in a minute. But if J is bigger than 1, this clearly doesn't make sense because this term's going negative, and you can't have a negative profile of the cell volume fraction in the far field. So if J is bigger than 1, you get a single exponential, and it's the one with the positive sign of the square root from the quadratic for damped simple harmonic motion, and that gives you the wave speed in that case. So this thing is only the fast decay rather than the slow decay if J is bigger than 1. So there is a clear complementarity between those two situations. Okay. So far, the explicit examples I've written down have been semi-linear rather than quasi-linear. I haven't had a nonlinear diffusion term. But fortunately, in terms of the traveling waves, you don't have to do any extra work. And the reason for that is the fairly well-known transformation at the top. If you change from Z to zeta, you map the quasi-linear case to the semi-linear. And what it does is lump together the two nonlinearities into the source term at D times F. So as long as you can understand the semi-linear case for general nonlinearities, you get the quasi-linear case for free, although you've got to unpick the transformation at the end to understand what the profiles are doing. This cubic nonlinearity case is kind of famous because all the exceptional connections are explicit in the phase space, and it corresponds to a nonlinearity Igor's had earlier. But anyway, that gives you this sharp transition. It tells you when you've got to push front and when you got pulled. So as A varies, as A increases, in effect, the nonlinearity is getting stronger because of the cubic term. So you're more likely to be pulled. Okay, so now I actually get to something I've hinted at several times, which is the phase plane analysis. So the equation we're dealing with is the one at the top. That's the semi-linear case. But as I've said, I can then unpick it and get quasi-linear. So I'm wanting a connection that takes you from 1 at minus infinity to 0 at plus infinity. So the stable state overrunning the unstable one, because C will be positive. And then the various situations you can get in terms of the far field, which is the way to classify this, because it tells you whether it's pulled or pushed in particular. In the non-Lipschitz case, there aren't any relevant solutions. You can't connect anything forward at plus infinity. I will mention later what can happen. The famous case corresponding to Fisher and things is the borderline case where P is 1, and then you have got, in the usual way, in the far field, damp simple harmonic motion. So you get two possible exponentials if C is bigger than 2, a stable node. If C is equal to 2, you get the degenerate stable node with the resonance thing with the Z. And if C is less than 2, you get a stable spiral, so the thing doesn't stay positive and doesn't make any physical sense. That comment I made earlier about Gompertz and things, that is the best studied case, but is also non-generic because it's sitting between the two generic scenarios. So if P is bigger than 1, if the minimum wave speed has exponential decay, which is where the first and second terms in the ODE balance, and if the waves that are going faster decay algebraically, which is the second and third terms balance in the far field. But these ones will only appear if the initial data has this decay rate. So you won't, for any sensible setup, it's highly non-generic. Okay, so you can think of C dagger as a eigenvalue, which is also what happens for the stable connections. Okay, so incidentally, the color scheme is going to reappear on the phase plane. So there's the slow decaying thing in red, there's a fast decaying thing in probably light blue, and then there's the purple thing, which is the degenerate node case. So what happens when the nonlinearity is such that you get a pulled front? As you reduce the wave speed, if C is big enough, you go in along the slow decay direction, the red curves. The light blue ones are the fast decay ones, which appear in the bottom case. As you keep dropping down C, and then eventually you hit the degenerate node, and that is how fast the wave goes. Because if you drop it any further, you go in as a spiral, which is both unphysical because it goes negative, and it's also unstable because it's non-monotonic. The push case, conversely, the first picture is the same. If C is big enough, you're still going in with slow decay. Then you'll hit some critical wave speed where you go in along the fast direction. And then if you go beyond that, but still C bigger than 2, you still have stable node, not a stable spiral, but you come in from behind. So again, goes negative and non-monotonic. So the speed you actually see in that case is C dagger. Okay, so I'll come back to that case, which I've described in some sense as non-generic, and I'm going to fill in the picture around it. So this is my second description of how I go about trying to understand this kind of problem, which is to classify the possible behaviors in the relevant asymptotic limits, which in this case are zeta goes to infinity or zeta goes to 0, depending on whether there's some finite cutoff. And you need to do that in both directions. So the wave back, for example, zeta goes to minus infinity, and when the wave front, zeta goes to plus infinity. So I've recorded my recipe here. The first comment is the thing that I only need to deal with the semi-linear case, but then I need to unpick the transformation back to the quasi-linear one. And then the recipe goes as follows. Just as I strip down the PDE into its component parts, I do the same for the ODE to identify what balances you can get. Once you've identified a possible balance, you need to check self-consistency. And what I mean by that is you've crossed off a term, you've extracted a possible behavior based on crossing it off, but then you bung that behavior back into the term you've omitted and check it really as a negligible term. So I've done one example of that at the bottom, and then the rest I'll just omit all those details. Next step is to count the number of degrees of freedom. So you're thinking about a boundary value problem set up for the traveling wave ODE. So you need to know if it makes any sense. So the number of boundary conditions you're imposing at each end, for example. and then finally check the entire picture. And by that, I mean, I'm going to be dealing with general values of the exponent Q, and then I'm picking those into general values of P and N. And I want to check I have filled in parameter space in a sensible way, that if there are gaps, you can make sense of why there are gaps, and you can check the different regimes do join up. Okay, so the one case I'm going to actually give the details of is the wave back. So dealing with V, I'll explicitly do the simple case where I assume the second derivative term is negligible. So the balance between the other two terms tells you that this is a possible behavior. Okay, so algebraic dependence on zeta. So how does self-consistency go? Well, if you've got algebraic behavior as zeta goes to 0, then the second derivative will be much bigger than the first derivative. Okay, if it was zeta to the -1, then the first derivative is zeta to the -2. But the second derivative is zeta to the -3, so it would dominate. So for this thing to make sense, zeta has to go to infinity, and because it's a wave back, that means zeta goes to -infinity. Once you've seen that, it's clear that this coefficient has to be negative for this balance to make sense. So we're always thinking of C as being positive, so that means this is only going to be relevant if Q is bigger than 1. So this balance is a self-consistent one if Q is bigger than 1. I then do the degree of freedom count. So zeta is going to infinity, and this is autonomous in zeta, so you can add on any constant which would correspond to a translation of zeta. So that's certainly one degree of freedom. The other possible degree of freedom, if you linearize about that behavior, essentially balances the first and second term, so it would be of this type. And again, to do that properly, you need Liouville green. But the point is zeta is going to -infinity, so this thing would be blowing up. So the second possible degree of freedom from the second order ODE is excluded, and you're only left with one, therefore. And then I have to unpick what that means for the original PN problem rather than the Q problem. And you do, if you go through reversing the transformation, you see there's two different situations. If P is bigger than 1, this is a fat tail, an algebraic decay at -infinity. Whereas if P is less than 1, you're hitting, V is hitting 0 at some finite location, which is being translated to be Z equals 0. Okay. So that will be the first case on the next slide. And I'm now trying to piece everything together by doing each of the possible balances. What time was I supposed to start? It was 11, wasn't it? Yeah, right. So the first case is the one I've just gone through, and that's recorded at the top. So I'm now filling in Pn parameter space based on the possible balances. So we saw there were two regimes in that case, both with algebraic behavior, but one of them, the vertical shading, which throughout is going to be fat tail stuff, algebraic decay at -infinity, and then the horizontal shading is where it hits close packing at some finite distance. And that was 1 degree of freedom. So the next possible balance is balance between the first and the second term in the ODE, and you find that doesn't work because we want C to be positive throughout. But that balance will appear when I do the wave front rather than the wave back. Right, the next possible balance is the one where you ignore the convection term, which corresponds to ignoring the time derivative in the PDE and is associated with the singularity I referred to much earlier. So you get this possible parallel behavior. And again, in two different cases, a sharp interface, so a free boundary problem in the first case where it gets close packed at some finite distance, and a fat tail in the second case where it decays algebraically. So the shading on the picture fills in that information. And that, I hope, clarifies one of the comments I made earlier about my recipe, that making sure the whole thing fits together. There's a clear transition between the picture at the top and the picture at the bottom. The two different shaded regions join up okay, and the dividing borderline is the same in both cases, n+1. And that's a 1 degree of freedom branch as well. Which incidentally, the 1 degree of freedom ones are typically the ones you want because it makes the boundary value problem correctly specified. There's one final case which will actually be very relevant later, which is where the dominant balance is simply the second derivative term. So it's a Stefan type balance if you're familiar with free boundary problems in that sense, except it's the opposite way around. You're pumping in material at a rate J rather than removing it. But I record there the situations where that can apply. And again, horizontal shading, close packed at some finite distance, vertical shading, algebraic decay. Okay, and again, coming back to this thing of making sure everything holds together, if you think of these as being one single branch, because it's the 1 degree of freedom one, it disappears on p equals m minus 1, so it's got 1 degree of freedom. And then this one has 2 degree of freedom, but disappears on the same curve. So it does make sense in terms of the combined picture. If you think in terms of bifurcation theory, you've got 1 degree of freedom and 2 degree of freedom. They're disappearing on a fold along that critical line. So mathematically, you'd normally exclude because you'd want the most regular free boundary setup, but it has a clear physical meaning in this case, which I've referred to, which I've alluded to already. So the region behind that curve can be, behind the wavefront can be close packed. There's a thing called contact inhibition of cell division. So if you think of once this close packed no division, cell division occurs, then J would be 0. But certainly with tumors, the big problem with tumors is they're not contact inhibited. So you would be driving growth through cell creation behind the wavefront. Okay, so that's everything I need to say. I am going to say about the wave packs in the context of the ordinary differential equation. There's going to be extra things to say for the PDE. And in particular, there is a regime, the unshaded region, where there doesn't seem to be any sensible traveling wave scenario. Okay, so now exactly the same kind of calculation for the wavefront. I need to remind myself what I wanted to say. So it's kind of clear, I think, from the phase plane that in the situations the phase plane is appropriate for, which does depend on the range of exponents, you've got a saddle point at u equals 1 and typically a node at u equals 0. So there's only one curve coming out of the saddle point that can connect with the unstable state. So that is giving you an initial value problem from minus infinity. But there's a proviso to do to that, which is to do with the things I've just said about whether you can pump in material at the wave back or not. But if you think in those terms that you're solving the thing as an initial value problem from minus infinity, you then need to think through what can happen at the wave front. Well, you can either have 2 degrees of freedom there, which are associated in the p equals 1 case with the fact you've got a stable node with 2 different decay rates. We've seen that already. If you come in along the slow decay branch, then you need to fine tune the initial data to have exactly that form. So that's one thing that can have 2 degrees of freedom, and you don't want it for that reason. The other one is where you overshoot, so you hit 0 at some finite distance, and that is the Stefan problem, where you're removing mass at a free boundary. So there is now mathematical biology literature about doing traveling waves for Stefan problems. You have to work quite hard to cook up a meaningful scenario where you're removing material at a point, but I will include that in my classification. The most important scenario for my purposes, though, will be the 1 degree of freedom case, where you're in effect determining the wave speed as an eigenvalue, because otherwise the problem is overspecified. So that's partly why I'm keeping count of degrees of freedom. Okay, so go through the same rigmarole as before. The first of them is this balance between where you ignore the diffusion term. You can get algebraic dependence on zeta, but there is an important difference from the previous case that the exponential I referred to before has the possible second degree of freedom. This time it's allowed because it's exponential decay rather than exponential growth. So that's a 2 degree of freedom branch, and that corresponds to initial data of the right form to pull the wave at that particular wave speed. The second case is the one that doesn't occur at the wave back, so this balance between second derivative and first derivative. So again, you get power law forms in terms of Z, and they are familiar if you've dealt with the porous medium equation. So this is the local behavior at the sharp front associated with the porous medium equation and is 1 degree of freedom. For the fast diffusion case, it's algebraic decay. You've got to be careful how you patch that into the PDE, and that will be implicit later. But as it stands, here's the scenario. Sharp wave front, so a true free boundary problem, and then fat tail in the other wedge. Next case is again the quasi-steady case, if you like, the balance between second derivative and the source term at the wave front. So similar looking form from before, the power law dependencies, but now because the sign has changed on the right-hand side, the regions of validity also change. And they're recorded there. And again, sharp front and fat tail. And that one presumably joins up with something. No, that's not the one that joins up. So I should actually go back quickly. So recall the one I didn't do in detail at the wave front, because the same as the wave back in some sense, the transition is at p equals n plus 1. Same is true here, and you'll see the p equals n plus 1 applies in the bottom picture here too. So this you think of as being a bit like a Stefan branch. It's not finite flux, but it is a 2 degree of freedom situation. So you think of it as being something to do losing mass at the wavefront. And the final case is the conventional Stefan, where the balance is simply the second derivative goes to 0. And that is the same as the wave back. And again, I go back to that. So you lose that one at p equals n minus 1. At the wave back, that was a fold where 2 different branches annihilated. In this case, it's a transition to this top picture here. So these two you can think of as forming a single 2 degree of freedom branch, which fills in the whole of parameter space. Now it's the other two that annihilate. One of them, the first one was 2 degree of freedom. The second was 1 degree of freedom. So those join up at p equals n plus 1 and annihilate along a fold. So I then claim you can piece together kind of the whole picture. If p is bigger than n plus 1, you've got a wave that goes faster than the critical speed. So you're only ever going to see that if you choose the initial data to have a very special form. For fast enough decaying initial data, you get the branch 2, which is the most familiar one, the minimum wave speed. And then if c is smaller than the critical speed, you lose mass at the interface, you've got a Stefan type branch. And there is this regime associated with the non-Lipschitz nonlinearity where you can only get Stefan branches. There aren't any others because the 1 and 2 have already annihilated. Okay, so in this regime, p less than n plus 1, we've gone below where 1 and 2 exist because they've met on a fold, but it's known the PDE does have solutions. So you've got a scenario where you know that the time-dependent problem must have some sensible large-time behavior, but there's no traveling wave it can evolve to. And that's probably the next thing I'll come to. So I think that probably completes my discussion of the ordinary traveling waves, unless there are any questions about that. Okay. Oh, yes, I have summarized them, which may or may not help. So there are 4 types. I can explicitly extract the regimes in which they exist. So they're the inequalities at the top. So 3 of them involve moving boundaries, the 4th doesn't. So you can get moving boundaries both at the front and the back for a certain range of nonlinearities. You can get ones at the front, as in the porous medium equation, in the second set. You can get a close packed region at a finite distance at the back in the 3rd set, and then fat tails at both ends in the 4th set. So I claim that completely classifies the possible traveling waves of the type in which I'm interested for the full ranges of exponents. Okay, but I haven't dealt with everything. I've only dealt with the ODE. I now need to go back to the PDE and check regimes where there aren't traveling waves but there are solutions. Okay. So I call these extreme pushed and extreme pulled. So I start with extreme pulled. So remember, pulled waves are dragged forwards by the low concentration region ahead of the wavefront. So in Fisher's equation, that effectively means you just got the heat operator. For the power law cases, you've got a slightly more complicated situation. But so that you can't linearize anymore because of the degeneracies in the nonlinearities. But you can still write down the small u dominant balance from the PDE. So that's what's recorded in the third line on this slide. So this introduces another very familiar concept in dealing with these kind of problems. I mean, this kind of cliche, but the first thing you look for is traveling waves, and the second thing is similarity solutions. So the full PDE doesn't have any similarity solutions beyond traveling waves. But this reduced form does, because it's got a scaling invariant. So that balance in the PDE admits a scaling self-similar solution, which is recorded on the middle of this slide. And the thing you then immediately check is whether that's consistent with our previous picture. So that's saying the spatial variable scales with a particular power of t. So if it's to make sense relative to the fact that we've lost traveling waves which grow like t to the power 1, this exponent better be bigger than 1. And you find that does fill in a gap. That gives you a continuous transition between the region I filled in with traveling waves and this new regime. And the relevant constraints are the ones recorded at the top of the slide. So again, this situation where there's no traveling wave, but there is a PDE solution. The self-similar solution G of eta, so it's the profile of the concentration ahead of the wavefront satisfies a different type of second-order ODE. You can't analyze it the same way as the traveling waves because it's non-autonomous. But this is, I think this is quite a nice free boundary problem. In fact, so as eta goes to infinity, you need to have the power law decay associated with fast diffusion. That was the fat tail I recorded very early on in the talk. But matching back, so this is the low concentration region, matching back to where the concentration is order 1, this thing better blow up. So this is in the matched asymptotic sense that you've got an inner solution that's blowing up from a small value and joins up smoothly with an outer solution, which decays down in this form. And we'll see that on the next slide, I think. So this is a free boundary problem. Eta naught needs to be determined as part of the solution to this problem. And then that you think of the propagation properties being associated with this quantity determined as the free boundary and the superlinear power law. So no longer a traveling wave, but something a bit like it. It just goes much faster. So what is the wave profile? It's what's often called a phase wave. So the thing is moving very fast. So if you think of C as being S dot, the first derivative term multiplied by C is much bigger than the second derivative term. So the dominant balance is of the type I've recorded at the top. So the wave profile is determined by that ordinary differential equation. And because it's first order, it's easy to check that matches forward. So as zeta goes to plus infinity from that initial value problem, you get behavior that corresponds to this algebraic behavior as eta goes to eta 0. So that's PF bigger than 1. If PF is actually equal to 1, you do get exponential growth of the type we saw yesterday from Malthusian growth, but rather different reasons. So in that case, you don't get a distinct wavefront. The entire thing is dragged forward by the far field behavior, which is recorded there. And the profile of the wave is this simple ordinary differential equation here, rather than corresponding to what's on the top of the slide. So that's a much more diffuse wavefront. The previous case, you can see a wave profile as determined by the ODE at the top. So rather similar to ordinary traveling waves, this one completely different, a very diffuse profile. Everything X entirely scales with the exponential. Okay, so that was extreme pulled, where the low concentration behavior, incidentally, I'm going to finish significantly early, but that's okay, I think. where the behavior is dragged forward entirely from the low concentration region. I should make the forewarning comment that you may get different information from the wave front and the wave back. So when you get to the end, you've got to combine the two pieces of information to give the overall conclusion. I'll comment on that briefly. So extreme pulled is the case I think is least recognized, where the thing is driven by the trailing edge rather than pulled forward by the leading edge or determined by the entire wave profile, as is the case for conventional pushed. So what happens now, I'm afraid this is a very poor diagram, but if you remember my V diagram from the quasi-steady balance early on, with the minimum in it, where it's trying to close pack, but not quite succeeding, that corresponds to region A here because U and V are opposite ways up. So A is the outer region, and it's this balance I alluded to much earlier on. Since I've got time, let me go all the way back. So this is why I have to do these things this way, by piecing together different pieces of information from the start. So this was the scenario I'm talking about in terms of V. So that ordinary differential equation has solutions of that type. In the first instance, you rule them out because they're singular, but you can now use them as a component part of the full profile. Okay, so that's region A, it's recorded here. What it doesn't tell you is what S is, right? So S is where it's going to be the wavefront, and it's the transition thing where this thing blows up. And I'm going to have to determine it by matching into the inner region. So if you're familiar with matched asymptotics, that will be a familiar concept. If you're not, it's a matter of making A and B join up in a smooth fashion to give you a sensible transition between the two different regions. Okay, so S is undetermined by this setup, but it does have a scale invariant again. So V scales with S, as does X, in a form that's recorded here. The matching condition that's going to end up determining how S evolves is this one here, which is telling you, in effect, the flux of material, the number of extra new cells being driven by cell division in region A, being pushed into region B. Okay, and then the inner region, region A, the dominant balance, S dot is much bigger than 1 again, but now rather than the second derivative term being negligible, the source term is negligible. So the relevant equation is the one at the top. You need U to go to 0 at plus infinity, because that's the class of solutions we're looking for, overrunning the unstable state. And that means you can integrate once immediately. The constant integration is 0, as recorded on the 5th line there. Okay, so you know that you can match forward and determine the solution in this form, which in turn tells you the flux where it's almost close packed. So where U equals 1, you know the flux is proportional to S dot. And again, that's recorded in the line above that. So I need to match between this prescription of the flux into this prescription where the flux goes like S dot at U equals 1, and that is recorded in the previous line. So the ordinary differential equation that determines S in this case is the one recorded there. So that's easy to solve, of course. It's autonomous, etc., separable. And again, one of the first things you have to do is check the exponents work. So check this really is superlinear. So can fill in a gap where you've lost the conventional t to the power 1 traveling waves. And you find there are 4 cases. And the 4th is the one I'm least sure about. So this is one area I'd like a lot of rigorous help if anyone's interested. So there's a range of P where you get superlinear growth as time goes to infinity. And for the record, the relevant power law is recorded there. And the transition back to the traveling waves is exactly where you lose the traveling waves. P is n minus 1. The borderline case P equals 0 is another one where you get exponential growth instead. And then there's a third case below that one, below that dividing line, where on the basis of this analysis, the wavefront will hit infinity at finite time. And that's to do with the singularities in P and N. So you don't expect this regime physically, but I think mathematically this one makes sense. I'm not sure about this one. So in this regime, the ODE doesn't make sense. So the simplest possibility is that U does actually hit 1 in finite time. The solution will certainly exist for finite time if U starts off less than 1 everywhere, but then instantaneously shoots out to infinity as soon as that happens, because you're pumping in too much new material. So that's my suspicion what happens in that fourth case. Okay, so I am actually nearly done. So there is a couple of summaries now based on combining the information from the ODE and the PDE. So again, trying to piece everything together. Most of this picture you've seen before, but there's 2 changes. One is I've excluded a region at the top with the PDE arrow. There is a traveling wave in there, but you find if you try and patch that into the far field of the PDE, there's no solutions that do that. So that top triangle with the dash straight line on the edge of it, the ODE is fine, but if you've just done the ODE, you haven't got the right picture. So the claim is you've got non-existence there. And indeed, the solution instantaneously extinguishes. It just diffuses out to infinity at 0 time. The 2 regions to the left of that are ones we saw in the traveling wave. So this dividing line here is the one that appeared from the traveling wave analysis. So you've either got a free boundary problem, a sharp front on the left-hand part, or where I put diffuse, that's the fat tail situation. And then the new regime, which didn't appear in the traveling wave, so rather removing something has filled in something. On the diagonally shaded region, the growth rate is superlinear. And on the horizontal straight line, it's exponential rather than algebraic in time. Right, and then below here, let's say I'm not going to emphasize P too small, the non-Lipschitz case, but over here, there is a solution. You don't have the non-uniqueness because the diffusion term is lifting the thing off at infinity. You can't hold it down for finite time. So over there, it lifts off at infinity, and you get U goes to 1 uniformly in time. Whereas over here, M is sufficiently large that the compact support thing of the porous medium equation maintains the Lipschitz non-uniqueness scenario. But there are also one special case of that is the ordinary traveling wave. Okay, so the wave back. This is a picture I want to pause on because it does make the strongest connections to the things I talked about yesterday. And let me start with those. Actually, let me start with the bottom picture. So recall the claim is that if you've got a close pack region behind the wavefront, you can pump in material through it. And that's to do with cell division being maintained in the close pack region. So you do have this kind of complementarity thing that you have one governing equations where n is 1 and something else where n is less than 1. So I haven't talked about the former of those, but they would determine the flux you were driving in. Okay, so down here, the horizontal shaded bit is the situation where things are cleanest. Here you can drive away from behind by inputting material from cell division behind the wavefront. I've said Stefan here to make the connection with that class of free boundary problems, but I emphasize it's the opposite way round. You're gaining material, not losing it. So here the solution has to be sharp. So the claim is you necessarily develop a dead core in that case. And again, I would like to know more about what the rigorous literature says about dead cores. Up here, it seems to be possible to get the same thing, but you would need to start off with a close pack region. So the question in that region is whether the thing can touch down, can quench in finite time. I think I probably suspect at the moment it can't. So this is a more artificial scenario where you have to start off with close packed. But I repeat the point, I would like to know what's known about quenching. So that's cell division within the close pack region. The top picture would correspond to complete contact inhibition where you've got a sharp front. So you're not introducing any extra material. And then you do get a perfectly sensible scenario in the horizontal shaded region of a traveling wave. Above that, you've got the fat-tailed ones at the wave back, so just algebraic decay as you go backwards. So you're never hitting close packing in the vertical case. In the horizontal case, you are, but you're not injecting any extra material there. The upward diagonals, the superlinear regime is the new one I've gone through the details of, the extreme push case, where there's no traveling wave, but there are PDE solutions, and they propagate the thing much faster than linear. And then the other diagonals are where the solution hits infinity in finite time. And then finally, this non-existent wedge where I haven't been able to find anything that makes any sense. So that's kind of counterintuitive. It's sort of odd that the non-existence regime sits between two where there does seem to be existence. I have a certain amount of intuition of that, but I keep forgetting what it is. Right, I think this is the final slide, possibly, yes. Right, so to try and wrap up what I've got and what's new and what's different. So the first set of inequalities are where, in terms of the semi-linear setup you can get to from the quasi-linear one, the linearization is trivial. So the U to the Q at the wave front vanishes relative to the linear terms. So Q is bigger than 1 is the way to think about that, which means the only possible scenario is pushed because there's no sensible linearization where you could get a pulled wave. So that regime is a rather clean one where you get pushed constant speed traveling waves. The case that's been by far the best studied, in particular because it includes Fisher KPP, is the one in the second bullet point. And that's the only case where you get the conventional pushed against pulled dichotomy, the two different scenarios, depending on the nonlinearity. So the claim now is that that's in some sense entirely non-generic because it's a borderline case in exponent parameter space. I mean, that said, of course, there's maybe good biological or physical reasons that you should sit on that dividing line. So whether you class it as exceptional or not exceptional depends on your viewpoint of the modeling. The most significant additional stuff is the superlinear growth stuff. And that can be driven either from the wave front or the wave back. And the first comment is something I alluded to before. You've got to do both ends and then see how you put them all together. So if you have something that's nominally both extreme pushed and extreme pulled, which is possible, whichever drives the wave fastest wins. And then you have to join up, you have to do matching into the other limit to make everything join up. But possibly more interestingly, the wave profile you get in the two cases corresponds to a different balance, right? So you are thinking of a region local in space where you can replace X in terms of Z, but the wave speed's no longer constant. So there's an S dot rather than a C. Right, the first case is familiar for other reasons, very familiar for other reasons. If you drag a wave forward very fast by having slow decaying initial data, the balance you get is the phase wave form where you're balancing the first derivative against the source term. Okay, we saw that earlier, but it's arisen in many contexts in the literature in the past. So those phase wave cases are very well known. The wave back case is the opposite dominant balance, where it's the second derivative against the first derivative. So that's, I think, less familiar and is a different type of wave profile. And then my concluding comment is, as will have been at least implicit, everything I've said is formal. I think there are a number of questions for rigorous analysis in this context, in fact, a considerable number. And also, if anybody's keen on numerical approaches to these kind of free boundary problems, please let me know that. But I will finish there. Thank you.
Much.